So everything you've ever touched, every material you've ever held, every device you've ever used is made of atoms. So the copper wire in your electric cables, the silicon in your circuits in your computer and your solar panels, the lithium in your batteries, the hydrogen in your fuel cells, the iron in your steel beams, the oxygen in every breath that you take. All of these, every substance that exists is made of atoms. So in the electricity video, I introduced electrons. These are tiny negatively charged particles that flow through conductors to create electric current. In the periodic table video, I introduced the elements. There's 118 of them on the periodic table, and they make up all the matter in the universe. But I've never stopped to explain exactly what an atom is at the most fundamental level, and how atoms combine to form molecules, and why that matters for everything from the air you breathe to the batteries that store our clean energy. So this is what this video is about. My name is Dr. Colleen Spiegel, and this is the Tesla Institute. So an atom is the smallest unit of an element that retains the chemical properties of that element. So there's three fundamental components. And I think we've all heard of these, but let's reiterate them. We have protons, neutrons, and electrons. So protons are your positively charged particles. They're located in the nucleus at the center of the atom. The number of protons in an atom's nucleus defines what element it is. So that number at the top of your periodic table, that's the number of your protons in that element. That's called the atomic number also. So hydrogen, if you look at your periodic table, hydrogen has 1 proton. The atomic number is 1. Carbon has 6 protons. The atomic number is 6. Copper has 29 protons. That atomic number is 29. And the periodic table is organized, right, by atomic number, like I just mentioned, from hydrogen at the number 1 position to organesson at number 118. So neutrons are electrically neutral particles, so they're not positive or negative. They're also located in the nucleus along with the protons. And the neutrons do add mass to the atom, but don't affect its chemical behavior. So the atoms of the same element can have different numbers of neutrons. And these are called isotopes. So carbon-12 has 6 protons and 6 neutrons. Carbon-14 has 6 protons and 8 neutrons. Both are carbon, both behave chemically like carbon, but their different masses make carbon-14 useful for radioactive dating. So of course, there's electrons that are negatively charged particles that occupy that space around the nucleus. And they're in, if you look at our traditional Bohr's model, they're in electron shells or orbitals. They're extraordinarily small compared to protons and neutrons. They're about 1,836 times lighter than a proton. In a neutral atom, the number of electrons equals the number of protons, which is balancing the positive charge of the nucleus. So the nucleus contains protons and neutrons, and this is essentially where all the mass of an atom is actually concentrated. So if an atom were the size of a football stadium, that nucleus would be a marble at the center. And the electrons are those tiny specks orbiting somewhere in the outer seats. So the majority of an atom is actually empty space. And that's actually where you kind of start to get into quantum mechanics. But this is genuinely counterintuitive because the solid objects around you feel solid to us, right? And this is because of the electromotive forces between the electron clouds, and it's not because matter is actually densely packed. So the chair we're sitting on is mostly empty space held together by electrical forces. And if you remember back in our periodic table, we looked at the atoms in the chair at the start of the video. So the most important electrons in any atom for chemistry and energy are the outermost ones, right? So in this channel, we're speaking a lot about energy and electricity. The electrons in the highest energy shell or orbit are called valence electrons, and those are the ones that are actually used in chemical bonding. These are the electrons that get transferred, shared, or given up when atoms interact with each other. So if you recall to our metallic bonding video, I explained that copper has a single valence electron, one loosely bound electron in the outer shell, and it's easily given up, which makes copper an extraordinary electrical conductor. In the periodic table video, I explained that lithium's single valence electron is what makes it the perfect battery material. So the valence electrons are where all of the chemistry, where all the action is happening. So atoms rarely exist in isolation. Under most conditions, atoms combine with other atoms to form molecules and compounds, and they're held together by chemical bonds. So a chemical bond forms when atoms share or transfer electrons in the way that gives each atom a more stable electron configuration. So this is typically to obtain an outer full shell. There are three main types of chemical bonding, and understanding all three of these types is essential for understanding how materials and energy technologies work and what we'll cover on the Tesla Institute. So ionic bonding occurs when one atom transfers one or more electrons completely to another atom. That atom gives up electrons and becomes a positively charged ion. The atom that receives that electron or electrons is becoming a negatively charged ion. So the opposite charges attract each other, which actually formed the ionic bond. So one example of this is our table salt. Sodium has one loosely bound valence electron that it gives up easily. That's because it's actually in the first column of the periodic table. Chlorine, being in the second to last column, needs one electron to complete its outer shell. So one needs one electron, one has an extra electron. So they are attracted to each other. The sodium transfers that valence electron to the chlorine, and both become ions, sodium positive, chlorine negative, and it's the electrostatic attraction between them that forms that sodium chloride. So ionic compounds tend to be solid, hard, and brittle. They have high melting points because ionic bonds are very strong. And they also have a tendency to dissolve in water, which actually releases the ions. This is why water conducts electricity, but it only can conduct electricity if there's ions in it. That dissolved ions carry the electric current. So for batteries, this really matters, right? The potassium hydroxide electrolyte in an alkaline battery conducts ions between the electrodes because it dissolves in water and releases potassium ions and hydroxide ions that can move freely in the solution. So the second type of bonding is covalent bonding. And this occurs when two atoms share electrons rather than transferring them completely. So they're sharing. Each atom contributes one or more electrons to the shared pair. Both atoms benefit from the resulting stable electron configuration. So water is one of the most important covalent molecules on Earth, right? Most of us, we're all humans, animals, we're all made up of mostly water. Each hydrogen atom shares a single electron with the oxygen atom, and the oxygen shares one of its electrons with each hydrogen, which forms actually two covalent bonds, because the result is H2O, right? There's two hydrogens and one oxygen. So water covers about 71% of the Earth's surface, and it makes all of our life possible. And in hydrogen fuel cells, it's the only byproduct besides waste heat. So carbon dioxide, CO2, is another covalent molecule. Carbon shares two electrons with each of two oxygen atoms and forms two double covalent bonds. Carbon dioxide is the greenhouse gas that makes reducing fossil fuel combustion, you know, a necessary step towards the clean energy revolution. And this is hydrogen fuel cells and our other renewable energy technologies don't produce carbon dioxide. Oxygen gas, or O2, is the oxygen we breathe, and in a fuel cell, it's used also. It's the oxidant. We have two oxygen atoms that pair with 2 electrons in a double covalent bond. Hydrogen gas is H2. This is the fuel for PEM fuel cells. Hydrogen is a diatomic molecule. There's always 2 atoms together that share 1 pair of electrons in a single covalent bond. So at the anode of the fuel cell, that H2 molecule is actually split by the platinum catalyst. It releases 2 protons, 2 electrons. This generates the electrical current. So covalent bonds are the bonds of life, actually. Organic molecules, and humans are an organic molecule. Every protein, every DNA strand, every carbohydrate is held together by covalent bonds between carbon, hydrogen, oxygen, nitrogen, and other elements. So we also have metallic bonding, and we covered this in one of our videos so far. It's a metallic bonding video. And so the metals in the valence electrons are not transferred to a specific atom, and they're not shared between specific pairs of atoms. They're actually given up entirely to the collective, and they form like kind of a delocalized electron sea that flows through the entire piece of metal simultaneously. So this is why metals conduct electricity, they conduct heat, and they're malleable and they're shiny, all from the same principle. And this is copper, which we've spoken about many times so far on this channel. This is why copper winds every transformer in Nikola Tesla's electric grid, and aluminum carries power along transmission lines across continents. So when 2 or more atoms bond together, they form a molecule. And the properties of a molecule depend not just on the atoms it contains, but also on how they're arranged and how they're bonded together. So water, which is H2O, 2 hydrogen atoms bonded to 1 oxygen atom, it's actually bonded at an angle of 104.5 degrees. That specific geometry is due to the oxygen atom pulling the shared electrons more strongly than the hydrogen atoms, and this gives water a slight electrical polarity. The oxygen end is slightly negative. The hydrogen ends are slightly positive, and this polarity is what makes water an extraordinary solvent. It dissolves ionic compounds like salt, and it enables, all types of chemistries and life on Earth. So carbon dioxide, CO2, 1 carbon atom double bonded to 2 oxygen atoms in a straight line. The linear geometry and symmetry of CO2 make it nonpolar, even though each individual carbon-oxygen bond is polar. So this geometric effect on molecular properties is one of the most elegant aspects of molecular chemistry. We also could look at hydrogen gas, H2. This is the simplest molecule in the universe. There's 2 hydrogen atoms and 1 shared electron pair. The fuel that powers stars through nuclear fission and PEM fuel cells through electrochemical oxidation. We could look at methane, CH4. There's 1 carbon atom bonded to 4 hydrogen atoms in a tetrahedral geometry. This is the primary component of natural gas, and when it's burned, it releases carbon dioxide and water. But this can also be used in a fuel cell reformer, so it has many uses as far as fuels and energy goes. It could help produce hydrogen as well for clean power generation. We have oxygen, O2. This is the oxidant that makes both combustion and electrochemical energy conversion possible. In fuel cells at the cathode, the oxygen molecules accept electrons from the external circuit and protons that go through the membrane. If you recall from the fuel cell video on this channel, water is the only byproduct. So every material that you interact with, every substance and energy systems that we cover on this channel is a collection of molecules or ionic compounds or metallic lattices made up of atoms that are bonded together in very specific arrangements. So the arrangement determines the properties, and the properties determine the applications that it can be used for. So understanding the connection between atomic structure and material properties is the foundation of everything from designing better fuel cell membranes to selecting the right alloy for pharmaceutical manufacturing equipment. So here's the connection between atoms, molecules, and clean energy world that I really like. And obviously, I have a fondness for. This channel is dedicated to energy and electricity. Chemical bonds store energy. So atoms form bonds, energy is released. When bonds are broken, energy is absorbed. So the difference between the energy of the bonds broken and the bonds formed in a chemical reaction is the energy released or absorbed by that reaction. So this is the fundamental principle behind every chemical energy source ever used by humanity. If you burn hydrogen, H2 reacts with O2, oxygen. The hydrogen-hydrogen bond and the oxygen-oxygen bond are broken. And now new hydrogen-oxygen bonds form, which create water. The bonds formed are stronger than the bonds that are broken. So energy is released as heat and light, and this is combustion. When a hydrogen fuel cell operates, the same atoms undergo the same transformation. H2 and O2 become H2O, but instead of releasing the energy as heat all at once, the fuel cell controls the reaction electrochemically. The electrons that would have flowed directly from hydrogen to oxygen in a flame are instead forced through an external circuit, and it generates useful current. So the energy stored in the chemical bonds of hydrogen and oxygen is converted directly to electricity at efficiencies far beyond what any heat engine can achieve. When a lithium-ion battery charges, the electrical energy from the external source is used to drive the lithium ions from the cathode back to the anode and store that electrical energy as chemical potential energy in the lithium graphite system. So when the battery discharges, those lithium ions move back to the cathode and they release the stored chemical energy as electrical current. So we have a common theme that I've been discussing in the last minute or so: charge, discharge, store, release. The chemical bonds in the electrode materials are the storage medium. The electrons flowing through the external circuit are the useful output. So when a solar panel absorbs a photon of sunlight, the energy of that photon knocks an electron from the valence band to the conduction band of silicon, creating an electron-hole pair. So the built-in electric field of the p-n junction sweeps the electron through the external circuit as electrical current. And the energy of that photon, which was originally released by hydrogen fusion in the sun, has been converted to electrical energy through the quantum mechanical properties of silicon's atomic structure. So energy is stored in chemical bonds, energy is carried by photons, energy is released by electrochemical reactions. So all of this ultimately comes from the rearrangement of electrons between atoms. So understanding atoms and molecules is not just academic background for the clean energy transition. It's the foundation on which every clean energy technology is built. Even components in the fuel cell, like the Nafion membrane, conducts protons because of the sulfonic acid groups attached to its polymer backbone. This is a molecular property that depends on the atomic structure of the sulfur and oxygen atoms in those groups. The platinum catalyst in a fuel cell that splits hydrogen molecules at the fuel cell anode works because of platinum's d electron configuration, which is determined by its position in the periodic table and its atomic number, which is 78. So this enables it to form temporary bonds with hydrogen molecules, and it lowers the energy barrier for electrochemical reaction. The silicon in every solar panel converts sunlight to electricity because of silicon's 1.1 electron volt band gap, which we discussed in the band gap video. This is determined by the quantum mechanical behavior of silicon's 14 electrons, which matches the photon energies of visible light almost perfectly. So the lithium in every battery stores and releases electrical energy because of lithium's single loosely bound valence electron, which is in the outermost shell of the lightest metal on Earth. It makes it electrochemically active and a very practical battery material. So we have atoms, electrons, chemical bonds, molecular structure. These are not abstract concepts. They're the engineering foundation of the clean energy world that we're building. So atoms are the smallest units of elements. They're made of protons, neutrons, and electrons. The valence electrons in the outermost shell determine how atoms bond with each other and how they behave chemically. So atoms combine through ionic bonding, covalent bonding, which is electron sharing. Ionic bonding is electron transfer. Metallic bonding is electron delocalization. And this forms molecules, compounds, and materials that make up everything in the physical world. So chemical bonds store energy. Breaking and forming bonds is the fundamental mechanism behind batteries, fuel cells, combustion, and photovoltaics. And every clean energy technology, from the silicon panel to the lithium-ion battery to the fuel cell, is built on the precise understanding of atomic structure and molecular behavior. This is why the Tesla Institute covers chemistry, physics, and engineering together, because they're not separate subjects. They're the same subjects seen from different angles. So subscribe to more on energy, chemistry, physics, and engineering, all connected through the thread of energy that Nikola Tesla spent his life trying to harness for everyone. Nikola Tesla believed electricity should belong to everyone. We're still working towards that vision. My name is Colleen Spiegel, and I'll see you in the next video.